So thank you again, and thank you, Professor Grzegorz, for excellent talk. Now I will continue discussing some numerical results and findings the associated quantum dynamics. So the starting point will be the Schrödinger equation, and as we remember, it can be written in this form. This is relatively simple, except the fact there is a non-trivial function k, and here there is a Heaviside step function, as well as the logarithm. This term, this step function, is necessary in order to guarantee the Hamiltonian is well defined. Now, the solution can be also found analytically, and it can be written in this form. Again, we have this non-trivial k function, and some another term, eta, and there is some ambiguity in this term because this is not just a normalization coefficient, but as we see, this is a function which have to be fixed in somehow. And this was also discussed on the previous talk. Now I will focus basically on a way of how one can provide a concrete example of the state of the wave function and how the numerical expectation value for the simplest operators P1 and 2 and Q1 and Q can be calculated. So first, we start with the situation our evolution becomes at t equals 0. This is the starting point, and as we see, our psi function is nothing but the eta. So this is the initial profile, which have to be determined. So the goal would be to fix two basic elements. The first one is the fiducial vector, and the second one are the boundary condition which guarantees this eta function can be determined. So from a numerical point of view, it is convenient to consider the fiducial vector in this form. So this is a Gaussian-like shape with the exponential term, which decays fast in infinity and also vanish at x equals 0. This term, this exponential term, would be very convenient in practical numerical calculation because it guarantees the k function, the terms related with the k function can be well integrated numerically. And this is also supported by intuitive point of view, since we start with some shape with some profile which is about some fixed point in X space. So having said that, the next step is the eta function. As it was discussed on the previous talk, a very convenient way of dealing with the problem is just to consider the situation in which we start with some point at the singularity and then ask about the evolution in time. So we start at t equals 0 and then continue the evolution. And if so, we have to fix the condition which guarantees our function really represents this situation. And as it was already discussed, at the classical level, in our language of the reduced phase space, the conditions are relatively simple. And these are the requirements that the object, the Q1 and Q2, goes to minus infinity in a very specific way, while the F0 function, which is also a very simple polynomial of momenta and t, goes to 0 once as t goes to 0. And also, as it was shown, these conditions can be translated on the quantum level and expressed in the language of the corresponding operators. And one can check that indeed, letting t equals 0, we can satisfy the third one, while the first and the second, so these conditions are slightly more complicated. Here are, for the record, I presented the operators under considerations. As we see, Q is, Q is a little bit complicated than P, and F0 is also given by this form with a Heaviside step function. Now, on the previous talk, it was presented a very general form of the eta function, satisfying the conditions that guarantees our evolution will be unitary and the state is well defined. Here, I will focus on a more specific example, and to be more precise, it is convenient to consider this simple function, namely the form in which we have the oscillating terms in exponents, and also quasi-normal mode represented by beta 1 and beta 2 functions. These parameters guarantees the function eta also vanish quickly in infinity, and this is a very good for numerics. So, having said that, we can, having the fiducial vector and the initial function eta, we can now go back and check this condition, guaranteeing we are in some sense close to the singularity. And as I said, it can be found that this condition is already satisfied, while these expectation values can be translated into these lambda coefficients of the normal mode in this function. Now, requiring we are close to the singularity, or this corresponds to the singular point, means that we should take very specific limits. So we should go with our lambda 1 and lambda 2 minus lambda 1 to minus infinity. However, from the practical point of view, it would be more convenient to keep them fixed. However, we can make them arbitrarily small in the sense that our large are negative. This way, we can approach the singularity. We can be arbitrarily close to the singularity. Still, our state is labeled by finite labels. So another thing which has to be done is the whole which was mentioned on the previous talk, namely the condition that the eta function should vanish when x2 is smaller than a fixed parameter, th. This is due to the unitarity, and I implemented this condition simply by redefining, by modifying our definition of eta function by multiplying with some auxiliary function, defined so that it is simply 0 for if if the arguments is smaller than a fixed parameter. This th is an additional parameter of our construction, and introducing th implies that our time is restricted only, is bounded also by its value. So we start with t equals 0 and then continue the evolution to th. And now in practice this function, this modification can be constructed simply by a quasi-step function which is continuous and equals 0 for if the argument is smaller than a fixed value, 1 if x is greater than th plus some additional parameter delta s, while in the transition region this function is approximated simply by cosine function. So there are two additional parameters. One is the boundary, is the limit of our term, and the second one is the parameter delta s. Now, having said that, we can write down the function psi, and this is given by these two simple formulas. The only non-trivial what is non-trivial here is the integral over the k function, which have to be performed. Now, as it was mentioned on the previous talk, once we try to reach the singularity, so be exactly in the singular point, lambda k goes to infinity, to minus infinity, meaning the frequency of this wave or this one goes to infinity. Nevertheless, probability, the associated probability density is still well defined. However, we can also find that the k function given by the integrals over momenta, which I presented already at the beginning, is also a non-trivial function. So, so far everything seems to be well defined. Now, I briefly present the expectation values of qk and pk. This is a way to uncover the evolution behind our quantum model of the singularity. And for this choice of fiducial vector and the eta function, the expectation value of the P1 momentum, as it was mentioned in the previous course, is constant, and it is related with two coefficients, beta 1 and a1, while one can find numerically that the expectation values of P2 is an increasing function, which is what we really expect from analytical point of view. This behavior can be tested for number of various parameters labeling the state. Now, a slightly more difficult situation is for expectation values of Q1 and Q2. Here one can find that there are two terms in the expectation value. The first one is something which we can recognize as telling how close we are to the singularity. So letting, in particular, taking into account the expectation value of Q1 operator and letting lambda 1 goes to infinity, assuming that the other corresponding conditions are satisfied, we are really at the singularity. However, as I said, this would be not the case, and in practice, it would be better to keep this parameter arbitrarily negative but finite. But this is the constant, so nothing special here. Now the second thing is the function k of t, which also comes from the form of the operators, and one can find that this is a function given by the following expectation value. And what is important here, that even starting with this with our initial function eta, labeled by the parameter lambda k, this function, which in fact gives dynamics, yes? Okay, 5 minutes, thank you. Does not depend of lambda k. And maybe it is good to mention here that talking about the construction of this function is very non-trivial, because there are many integrals which have to be performed. The first is the k function, which is function which contains two integrals over momenta. Then we have differential operator acting on this, another integral, and two another integrals to get the expectation value. So in practice, I decided to use methods of integration based on Gaussian quadratures, modified so that it fits to the. This is well suitable to the our integrand, and partially these integrals are also checked by Monte Carlo methods of integration. However, these are highly insufficient for these integrals. And finally, these are example. This is example result showing that illustrating the function Qn, Q1. And as we see, what is interesting, the function oscillates, and this can be visible for various parameters here, delta s and delta equals 10 and 1.1, 0.1. And as we see, this is something familiar which one could expect on the classical level when we have an oscillating behavior near the singularity, because Q1 is our quantum equivalent of the logarithm of phase factor. So we have some oscillating behavior near the singularity.
What is
of
the y-axis? What's the vertical axis?
The vertical axis are these are values of this function, while this is time restricted by th.
The horizontal axis is marked Q1 of t. So the vertical
No, maybe this is not. No, Q1 of t is this is this function, but this refers to the vertical axis. The horizontal axis is t.
Okay.
And another example is increasing. Is to ask what will happen if we increase the h parameter, and once again check the dynamics. And what is interesting, that increasing th, the oscillations survive, and what is more, there are some regions where they are frozen for a while. I mean this one, and then they reappear. And now for Q2, which is also related with another scale factor of the universe, the situation seems to be, at least at first sight, qualitatively different. However, we can find also some oscillations. And if we go with th parameter from 10 to 30, then we can find that this behavior is very similar to expectation value of Q1. So there are oscillations. And summing up, the goal of this talk was to illustrate the formalism of the quantization of BKL singularity by constructing explicitly the wave function and finding the simple expectation value of the expectation values of the simplest operators. Here we started from the point representing a region in some sense close to the singularity, and